In the previous lecture, I showed how quanta make up the void and elementary particles and how quanta move in reactions from one particle to another and eventually become a part of the void. In this lecture, I will put this understanding in use to make sense of the cosmic expansion. The universe is so naturally present that we hardly pay any attention to it. Yet we should comprehend no less than the whole, otherwise our view of the reality remains incomplete, even incorrect. Cosmological questions are among the most significant in contemporary physics. What is dark energy? What is dark matter? Why do constants of nature have the values that they do? Why do we exist? So the hottest issues in cosmology are not only about the hypothetical called dark matter, but about the worldview on the whole. Although most of what we know seems sound, not everything is. Physicists measure and model expansion, but they hardly ask why the universe is blowing up, because general relativity, as a mathematical model of the cosmos, is not about causes and effects at all. The expansion is seen as an inborn and inexplicable attribute of the Big Bang, not a consequence of a still prevailing cause. However, the reason for expansion is worth reconsidering, because astronomical data on stars, gas clouds, galaxies, and voids are no different from any other data displaying the grand regularity, the universal patterns. Since the evolution of the universe includes all events, it cannot be a process in its own right. We should thus be able to infer from any event something about cosmic evolution. So let us do that. We see that the shining sun transforms matter into photons, but we do not see those photons that break out from the matter in pairs, as I explained in the previous lecture. Space consists mainly of these dark, weakly interacting photon pairs. This is to say, space does not emerge from nothingness. It unfolds out of the stars where matter transforms into the void. So, as the amount of matter diminishes, the expansion slows down and eventually the void will be everything that there is. This geometry of a universe that expands in this balanced way is said to be flat, and its density is called critical. The density of the universe is, naturally enough, critical. In contrast to this comprehension by thermodynamics, the standard model of cosmology does not explain why the density of the universe is critical, but the model is fitted to the observed flatness. And hence, the flatness seems like a lucky strike, or be mistaken as something designed. But the geometry of the universe is a dead issue when space stems from matter. As space stems from matter, we may abandon the assumption that the universe could decelerate, start to contract, and eventually collapse, for there is no force to turn the course of all events around back toward a big crunch. Evolution is irreversible. We may also disregard the possibility that the universe could billow out ever more rapidly by some unknown dark energy, for there is no fuel to power ever faster expansion. Distant galaxies will not recede beyond the range of light. In due course, the galaxies will cease to exist when all quanta bound in matter have been released into the vacuum. We can also discard the hypothesis that the vacuum might break apart, for there is no force to rip apart the indivisible and eternal photons. When all energy differences, forces, the causes of events have at last vanished, everything that can happen has happened. This ultimate fate, the end of time, is called heat death. So the ancient idea of the eternal element of everything limits interpretations of the data on the universe's evolution more sharply than many a model of cosmos.
What is gravity?
Bodies fall. Why? The cause is unknown. From the 16th century, the cause of gravity was speculated over and again until Einstein came up with an unparalleled perspective. There is no reason whatsoever for bodies to fall, for gravity is mere geometry. Bodies and light alike move along the optimal path, most favorable trajectories known as geodetic lines, unless disturbed or obstructed. Raindrops fall straight down to the ground unless the wind is blowing. General relativity, despite its success, cannot be the complete theory of gravitation because space cannot be a continuum but must consist of quanta as matter and light do. Gravitons can be theorized to mediate gravitation in the same way that the photons are known to mediate electromagnetic force. Then the gravitons would emerge from mere emptiness and when necessary, and disappear back into nothingness when no longer needed, like the virtual photons. So I'm saying that the virtual particle is a way of calculating, not a way of explaining. The fact that gravity is still an open question may simply imply that the track we are on does not lead to the goal. Since we cannot see the way forward, let us look back what Newton supposedly saw. What's actually happening when an apple is falling? Why a distant galaxy is receding and a nearby one approaching? From these observations, we should recognize a single law for all motions, just as Newton discerned the same law in the falling of an apple and in the orbiting of the moon. The whole universe is expanding because in numerous processes quanta break out from dense matter into sparse space. So distant galaxies are receding from us as they couple with the outspreading void. Conversely, our neighboring galaxy, Andromeda, is coming toward us because fewer quanta are entering between it and us than are streaming out into the greater universe. The apple falls earthward for the same reason. We may compare the void's motion to that of water. When water flows between the floating bodies, they move apart. And when water flows out from the gap between the bodies, they approach each other. While this analogy may sound questionable, it's worth keeping in mind that Maxwell used hydrodynamics when deriving his field equations for the void. From this hydrodynamic perspective, bodies neither attract nor repel one another, but bodies move because they couple with the flows of the void. This understanding of the vacuum as a substance is in line with our own experience. When the driver suddenly slams on the brake, our bodies continue in motion because we are coupled to the surrounding space, and when the driver steps on the gas, we sense the coupling in the opposite direction. That's inertia. We also experience the grip of the vacuum as centrifugal force. Physics textbooks refer to it as a virtual force, but the force feels very real, for example on a carousel. Similarly, for the moon to take off from its orbit as a stone shoots off from the sling, more and more quanta would have to enter in between it and the Earth. Conversely, for the moon to fall to the Earth, more and more quanta would have to exit in the rest of the universe. When the forces are in balance, there are neither causes nor effects. Then centrifugal force is said to tally gravity. Gravitational force is, like any other force, an energy difference. The denser the gravitational field, the local vacuum, the higher the difference relative to the sparse gravitational field of the universe. For instance, an apple falls faster here on Earth than on the moon because the difference between the universal gravity and terrestrial gravity is greater than that between the universal and lunar gravities. The thermodynamic theory maintains that the quanta flow so that any imbalance diminishes in the least time. Why would gravity be an exception? The apple falls straight down because the void moves toward a balance in the least time. The universe expands in every direction for the same reason, and astronomical data display the grand regularity, skewed distributions, spirals, S-shaped curves, network structures, straight lines on the log plots, that is the power laws, and even chaotic trajectories. Well, Newton acknowledged that he did not know the cause of gravity when contemporaries recognized instrumentalism in his law of gravity. Unless carrier of gravity is known, the theory of gravitation does not explain why bodies move, and hence remains only a model. Faraday inferred that the field lines of a body mediate forces, but failed to validate the link between gravity and electromagnetism. Indeed, gravity and electromagnetism are alike, but only now do we understand that unity. Photons mediate both forces. Gravity is a manifestation of the vacuum density differences that the flows of the paired photons are leveling off. Bodies move as they couple with these flows. The unpaired photon in turn mediate electromagnetism, as it says in the textbook, when evening out the vacuum gradients and vortices. Charges move and magnets rotate as they couple with these flows. By all accounts, the vacuum is neither virtual particles nor space-time geometry, but a real substance, the ether. In school, we are taught that when an apple falls, the gravitational energy associated with the height is converted into the apple's kinetic energy. Conservation of energy holds nearly, but not exactly. When the apple is on ground, the Earth is no longer the same as it was. Hence, its gravitational field is not the same as it was when the apple was still hanging from the tree. If we do not take the change into account, our bookkeeping of quanta will be inexact. In practice, the difference is negligible because the apple is tiny compared to the globe. On the other hand, for understanding the gravity, the difference is significant. If we do not discern it, we will erroneously believe the gravitational field to be no substance at all. Moreover, physicists take it for granted that gravity is an attractive force. Here on Earth, bodies fall vertically, sure, but horizontally, where Earth's gravity is constant, we experience the gravity of the whole universe. We sense it as inertia. The reaction to the universal gravity to acceleration and deceleration are opposite. While contemporary physics makes a distinction between gravity and inertia, gravitational mass and inertial mass could not possibly be different from one another because both gravity and inertia are manifestations of the coupling of a body with the same vacuum.
What are the fundamental forces?
Physicists and philosophers wonder why the four fundamental forces, gravity, electromagnetism, and the weak and strong nuclear forces, have the strengths they do. This puzzle is known as the hierarchy problem. Let us inspect this matter through the lens of time. With the universe expansion, energy differences diminish and eventually disappear altogether. At the end of time, there will be no matter left, as all quanta will have become part of the vacuum. Then gravity will be all gone, as there will be no matter to cause density differences in the void. Electromagnetism will likewise cease to exist, as there will be no electrical charges. There will be no weak force either, as there will be none of its carrier particles W-, W+, and Z bosons. And there will be no strong force, as there will be no quarks for gluons to link together. As the fundamental forces vanish with time, they may not have been fixed at the beginning of time either, but display the structures of the universe from the largest to the smallest, rather than dictating them. Paul Dirac thought that the immense ratio between the forces of electromagnetism and the gravity reflects the size ratio of an electron and the universe. But his large number hypothesis was not taken seriously, for the structures of the particles were not known down to the accuracy of one quantum, and the expansion of the universe was not understood as a process in which the sparse vacuum stems from dense matter, and the quantum was not recognized as the common denominator of everything. Eddington was also enthused about the ratios of the natural constants. As the story goes, Samuel Goldsmith, having listened to Eddington's passionate lecture about the meaning of the fine structure constant, asked his elderly colleague Hans Kramers, "Do all physicists go off on crazy tangents when they got old, I'm afraid?" Kramers assured him, "No, Sam, you don't have to be scared. A genius like Eddington may perhaps go nuts, but a fellow like you just gets dumber and dumber." Now we understand that gravity is feeble compared with the electromagnetism because the universe is huge and hence low in density compared with a tightly coiled electron. Similarly, the fine structure constant, the ratio of the electromagnetism to the strong force, expresses the electron's torus to the neutrino loop. The fundamental forces are outcomes of evolving universe rather than of chance or design. We have not just been aware of the physics that determines the natural constants, as Laughlin anticipates. The fact that is the cosmological constant, is so small tells us that the gravity and the relativistic matter, that is the vacuum, pervading the universe are fundamentally related in some mysterious way that is not yet understood. Now, we understand that the relativistic matter is the void, the universal gravitational field which attains and maintains balance with all matter in transformations of quanta. Thus, the anthropic principle is only a delusion. It is not so that we would not be observing the universe unless it had such and such properties as to enable us to evolve into existence, because the data relating to us disclose the same patterns as any other data. The grand regularity speaks for the Copernican principle, whereas nothing speaks especially about us. Granted, if the fine structure constant deviated from its value in the 6th decimal place as muon differs from the electron, life could not exist as we know it. The muon is no surrogate for the electron. It cannot withstand the test of time but transforms into an electron. The anthropic principle is teleological, all right, but the goal of cosmic evolution is not our existence. We're not here to perceive the universe due to the natural constants being what they are, but rather the reason for our existence and the reason for the values of the natural constant is the same, the least time quest for balance.
Why is the distant horizon uniform?
The temperature of the pitch black sky is virtually the same in any direction. The most distant galaxies too are scattered nearly evenly in all directions. Cosmologists are baffled about this uniformity. How could the temperature of space and density of matter on the opposing sides of the universe possibly have become equal when there is not enough time for a light to have traversed from end to end? This puzzle is called the horizon problem. According to cosmic inflation, the very earliest universe ballooned faster than light for a very short time, so that the objects which were initially close to one another and hence in thermodynamic balance maintain correspondence even when flung far apart. In this way, the early differences in temperature and density would have been significantly smoothed away over the expansion, although not altogether. Well, indeed, the cosmic background radiation temperature deviates from the 2.725 Kelvin average only about 10 in a million. However, is the cosmic inflation a tenable explanation of the largest scale uniformity? Is inflation a theory at all? How could it be falsified when its parameters allow for not one but many different models? Why bother to tune the parameters toward observations as the fit does not even explain the phenomenon? Although this criticism is on point, it is all the more important to understand the reason for large-scale homogeneity than to model it. Even if two things manifest themselves concurrently, like the same temperature at the far apart locations in the distant sky, it does not mean that one follows from the other. Neither are grapes ripe in one bunch because they are ripe in another. As they say, correlation does not imply causation. Rather than from extraordinary inflation scenario, the uniformity across the horizon follows naturally and necessarily from the universal quest for balance in the least time. Namely, Newton's second law of motion says the bigger a force, the faster the change in motion. This means, for instance, that the higher a temperature difference, the faster the rate of cooling. Thus, in due course, there will be only minute temperature differences, regardless of how high the differences were in the beginning. When the root cause is the same, the consequences manifest alike, even though they are not causally connected. Grapes independent of each other, are ripe at the same time because of a common cause, namely sunshine. Though the early differences in temperature and density have by now nearly flattened out, the process is still ongoing. A large difference in energy decreases rapidly and a small difference evens out slowly. For example, the most massive stars shine the brightest and for the shortest time, well below 100 million years. Small stars can glitter for over 100 billion years. Thus, over time, there will be only small differences, as is observed. Ultimately, everything will become the same regardless of what the earliest universe was alike. We know this course of history from familiar sequences of events. As an illustration, when a cake is to be divided as quickly as possible into smaller and smaller pieces of equal size, we will not slice it randomly. First, we will split the cake in half, and then halves, the halves and halves and halves. The division at the hand depends on all previous divisions, so that at any given moment the largest piece will be split next. The slices of the historical process are not in random directions relative to each other, neither are they identical, but unique. By the same principle, the early universe did not cool arbitrarily, but always fastest in the hottest site. This historical process is still visible in the temperature map of the deep sky. The temperature of the space is in every direction almost, but not exactly the same. The variation is only a few tenths of millionth of a degree. Moreover, one half of the sky is slightly warmer than the other. The halves and halves and halves, and even their halves, differ from each other in the same way. This regularity, dubbed as the axis of evil, and the cold spot in the southern sky are not merely coincidences to be ignored, but rather noted and understood as characteristics of causality. Halves and their halves and so on of the temperature map bespeak of a chain of least time events, the cutting up the cake in pieces. The pairs of galaxies and the pairs of galaxy clusters found at all scales also result from the same least time rather than random decimation of matter into the void. The big question of present-day physics is why and how matter gains supremacy over antimatter. Physicists theorize that the Big Bang produced both in equal amounts, and soon an enormous annihilation took place. By some miracle, there would have been an excess speck of matter from which the whole universe was formed. Physicists see the slight surplus as a sign of imbalance between matter and antimatter. They wonder what might have caused it, since it is explained neither by standard model of particle physics nor by general relativity. No energy difference between the matter and antimatter has been detected either. The masses and magnetic moments of protons and antiprotons are indistinguishable. Given that not only findings but also paradigm shifts have previously resolved great riddles, we ought to ask why we think as we do. Reduction is a standard method in science. That approach does not explain the excess of matter over antimatter because it detaches the particle from its environment and history. In those unnatural circumstances, handiness, the chirality standard of substance, plays no role, for there is no hand to shake. The standard of substance, being either matter or antimatter, is necessary for things to happen, not for stasis. In contrast, when the characteristics of matter and antimatter are to be determined experimentally in a test tube, so to say, expressively nothing should happen that could spoil the measurement. That's why the victory of matter over antimatter is indecipherable by reductionist approach. According to thermodynamics, one of the two equivalent options will inevitably win when the choice, one way or the other, paves the way to a balance. The victory of matter over antimatter does not allude to an imbalance, but on the contrary, the handiness standard of substance serves evolution toward balance.
What is dark energy?
The dark energy hypothesis stems from difficulties in accounting for the brightness of so-called standard candles, supernovae that flash equally brightly. Their flares have been recorded systematically since the early 1990s. Before the turn of the millennium, it transpired that the data did not fit into the Big Bang model of cosmology, where the density is critical and the cosmological constant is zero. Henceforth, it was conjectured that the expansion of the universe is accelerating. The cause of acceleration is referred to as dark energy because the scientists have no clue what it is. Rather than tailoring the standard model to fit the data, let us examine what is happening as the photons from an exploding star spread into the expanding universe. We see the light of a receding supernova getting dimmer and redder, much the same way as the siren sound of an ambulance fades in intensity and lowers in pitch. The detected amount of light is inversely proportional to the square of the optical distance to the exploded star. As the light is in transit from the past to the present, its color shifts not only due to the speed of recession, but also due to the weakening of gravity of the expanding universe. This account is not the tired light conjecture, but the gravitational effect on the color of light, which is also well known from general relativity. When the intensity of light depends on two factors, the data does not follow one straight line on the log-log scale, but with increasing distance and time departs more and more from the expectations of the standard model. By contrast, the thermodynamic theory of time leaves no room for dark energy, for the calculation complies with the data, even though it is not fitted to the data. There is no free variable to be tuned or tweaked when the age of the universe, about 14 billion years, is taken as given. The rate of expansion, known as the Hubble parameter, could not be other than the inverse of the age of the universe, because the distant galaxies are receding as time, that is, the quanta with the periods move from matter to the void. As the matter is running out, the expansion is slowing down. Hubble's constant goes down as time goes on. Indeed, our neighborhood of the cosmos, being the oldest, has the lowest average energy of substance. The gravity of galaxies, like that of the Earth, causes a red shift. The light coming from the center of a galaxy group is on average slightly redder than the light emitted from the rims. For the same reason, light shifts red when passing the early dense cosmos to the present sparse universe. Hence, the shift is indicative of not only the velocity of the receding galaxy, but also the decreasing gravity of the expanding universe. In this way, thermodynamics explains the supernova data without resorting to dark energy. The universe is not accelerating, but decelerating as it expands. How could general relativity be wrong? After all, it explains so much. The model indeed concurs with many kinds of data, but by what means? The more mathematical model is modified after the fact, the better it fits the data and the less it explains what's going on.
What is dark matter?
In the 1960s, the American astronomers Vera Rubin and Kent Ford noted that the orbital velocities of stars and gas clouds increase from the center of the galaxy toward the fringes, whereas the orbital velocities of planets decrease from the sun outward. It is assumed, based on the law of gravity, that the surplus of orbital motion of galaxies must be due to additional yet unseen matter. Fritz Zwicky was already offering the dark matter hypothesis in 1933 to account for the fact that the galaxies move relative to one another with great speeds. Our neighboring galaxy, Andromeda, too, is approaching us with a velocity of about 300 kilometers per second. Such a high-speed attraction between galaxies calls massively for existence of this mysterious form of matter. The Andromeda Nebula, moreover, spins so swiftly, just like the Milky Way, that it too must contain much more dark than luminous matter. All observations of the dark matter so far have been only indirect. What could the dark matter possibly be, since it is so hard to come to grips with? While the dark matter theorists cling to the hope of a big breakthrough, we can make a small point. The galaxy's orbital velocities do not oscillate endlessly, but seem to settle on a constant value far away from the galactic center. There, the orbital velocity depends on the galaxy's mass and a small acceleration, which shows itself also in the velocity dispersion of galaxies. Miraculously, the tiny acceleration equals the speed of light divided by the age of the universe. Is this universal acceleration just a cosmic coincidence, or does the universe have something to do with the motion of galaxies? This is a critical question, as coincidence is no explanation. Dark matter is only needed when the gravity of the ordinary matter drops below the universal acceleration. Nonetheless, ordinary matter ordains the distribution of dark matter in a law-like manner. How is this possible? Would not the visible and dark matter have separated from each other, say in collision of galaxies and at the birth of stars? The speeds of stars and gas clouds from dwarf to massive elliptic galaxies follows a power law familiar from the big data of diverse kind. Near the galactic core, there's a lot of matter, and since the acceleration is high, there is no need for dark matter. Further and further away, more and more matter is modeled as dark, which is to say, the more we look at the data through the standard cosmology, the more it seems that the dark matter exists for us and becomes more in itself. Let us liken a galaxy in the universe to a cyclone in the atmosphere, to realize that the galaxy rotates not in emptiness but in the expanding universe. A remote hydrogen gas cloud orbiting beyond the shining outer rim of the galaxy stars experiences gravity not only due to the galaxy but also due to the expansion of the universe. At first sight, this explanation for the missing mass may seem too simple. How could the galaxy possibly experience any force due to the rest of the universe, given that the matter on the largest scale is spread evenly about the galaxy? The thing is that although the matter is distributed evenly in every direction, that is to say isotropic, the distribution is not flat, that is to say homogeneous. Namely, in the nearby universe, matter is sparse, whereas it is dense in the distant early cosmos. Thus, there is a shallow density gradient across the expanding space from the nearby present to the far-off past. This universal gravitational field acts everywhere in a law-like manner, as stated in the Hubble's law. It causes the flows of the void to which bodies couple, and hence far-away galaxies move away from us and the nearby galaxies move toward us. The universal energy gradient from the dense past to the sparse present is a feeble force that is apparent only on the galactic scale. For instance, the solar system's orbital velocity about the center of the Milky Way is remarkably high, 220 kilometers per second, to stay in balance with both universal and local density gradients. There is no reason to impute the extra rotation and translation of the gravity of the dark matter. All matter is in fact visible, only its gravitational field, the paired photon vacuum, is dark, that is to say, transparent. A top stays upright when spinning fast, and having slowed down, it tips over. Why? The textbook says that the spinning top remains upright because its angular momentum is conserved. But no one knows why it is conserved, just as no one knows why linear momentum is conserved. There are equations without explanations. Now that we know the essence of the void, we know the reason for the top spinning is the quest for balance. The top spins steadily because then its position in the universal gravitational field is optimal, balanced. For the same reason, dwarf galaxies orbit the plane of a spiral galaxy instead of in random inclinations. If the top is poked, it quickly reorients to restore its balance with the void. If a spiral galaxy is punched with another one, the deformed disk of stars will realign to regain the balance with the void. A ray of light bends when going through the gravitational field, similarly to when passing through a glass of lens. However, the bending due to the visible matter of a galaxy is much larger than expected by general relativity. Zwicky had already spotted this discrepancy in the 1930s, but from such observations in the 1980s, it was concluded that the dark matter makes up about 4/5 of all mass in the universe. According to the least time principle, light bends almost 5 times more than predicted by general relativity. Thus, dark matter is not needed to explain the bending of light. How could general relativity be wrong? Has not the theory explained the bending of light coming tangential to sun from a distant star? Eddington was the first to make that demanding measurement during the total eclipse of 1919. Today, the effect of the gravity on the photon path is most precisely measured from how much the radio signal is delayed when passing by the sun to, for example, Venus and back. The photon's travel time is longer when passing through sun's gravity compared to in free space, just as it is in glass compared to air. The least time principle gives the correct value 195 microseconds for light passing by the sun. As we know, general relativity also gives this result, but in its case, the delay is calculated by a different equation than the one for the bending. Why does general relativity need two different equations for calculating the passage of one and the same photon? The bending of light is determined from the difference in the lines of sight to the star during an eclipse and a half a year later in the clear night sky. Although obvious, it's essential to note that the ray of light ends up at a different point on the ground when it has passed through the gravitational lens compared to when coming directly from the night sky. So, if the same ray is to be traced, the telescope should be moved by the distance corresponding to the change in direction between the two conditions. It is easy to grasp the relation between the change in direction and the telescope's displacement. Looking at your finger with one eye and then the other switching to the other, it seems that the finger is moving relative to the background. If this phenomenon called parallax is to be averted, the position of the eye, like the location of the telescope, has to be changed to match the angle from which the object is seen. Eddington did not take this into account, so the bending appeared smaller than it actually was.
What is a black hole?
If a star was so massive that even its own light cannot escape the pull of gravity, we would not be able to see it, reasoned John Michell in 1783. Such a star could nonetheless be inferred from the motion of its companions. The pioneer of astronomy, gravity, optics, and geology assumed that there are many dark stars in the universe. Nowadays, such a dark star is called a black hole. But we do not think of a black hole as a star, as Michell did, because general relativity is not about substance, but space-time. And we do not talk about the surface of a dark star, but an event horizon of a black hole. And we do not zoom in the dark star's nuclear reactions, but on the black hole singularity. However, is it not incoherent to posit that a black hole is a whole different thing than everything else? Moreover, modern physics asserts that the information cannot vanish, while it's an everyday experience that information disappears when its representation is wiped out. When a star becomes more and more compact, its matter transforms into neutrons. If the mass of a neutron star remains less than 3 solar masses, light can still escape from the surface where it cannot from yet more massive stars. When the density of black hole core increases by some 2 orders of magnitude above the atomic nucleus, gravity outstrips the strong force and the neutrons break down. Under these circumstances, general relativity no longer holds true, but points to the nonsensical singularity. Thus, we would need a quantum theory to bring conformance with the fact that the matter cannot condense endlessly. The quandary is that quantum mechanics in turn leads to the information paradox. Well, we can, however, escape the mathematical singularity and dodge the information paradox by acknowledging that the quantum's measure, the Planck constant, does not change under any circumstances. When the mass of a black hole exceeds the mass of a few tens of suns, gravity overpowers the strong force. As the paired photons of the gravitational field become as short as the gluons might as well disconnect from the quarks and connect to the surrounding photon fluid. As the neutrons break apart, the quarks of opposite handedness juxtapose and annihilate. Matter transforms into the void. Data from black holes is understandably scarce to justify one tenet or another. Nevertheless, the little that there are calls for interpretation. Where did the bubbles of X-rays come from that the Fermi Space Telescope detected in 2010? These incandescent bulbs of X-rays extend tens of thousands of light years from the center of our spiral galaxy. Did they form over the eons from the intermittent jets that the spinning supermassive black hole at the center of the galaxy emits? High-energy rays likewise squirt out into space from centers of other spiral galaxies. Neither eyes nor cameras can see the dark shine of paired quanta that the black hole ejects. Still, the emitted density can be detected as a gravitational wave. Such a density surge, a gravitational wave, was registered for the first time in September 2015. It started off when two black holes merged after spiraling about each other. It happened safely at about 1.5 billion light years away. By the time it struck the high-resolution detector at the LIGO Observatory, the huge tidal wave had dwindled down to tiny wavelets. When the gravitational wave arrived, the laser light reflecting back and forth in the detector's 4-kilometer vacuum tube momentarily passed through the wavy void. The principle of measurement is familiar one. By placing a glass plate in the path of light, the flight of time will increase. The glass is, of course, much denser than a gravitational wave, so the effect is much stronger than that due to such a wave. In contrast to this common sense explanation, general relativity maintains that the tube itself contracts a bit when hit by the gravitational wave. It's difficult for us to deduce from the data alone which description is true, but we must consider the whole. Why should we explain the gravitational wave differently from other waves? Why would it shorten the detector's tube rather than changing the vacuum density therein? Why would a wave of the void be, in a sense, different from a slab of glass? Questioning the interpretation of general relativity in this matter makes us realize that the mathematical model is no explanation as such. The more narrowly we focus, the less we see the bigger picture, and the less we understand the thing in question the way we understand other things.
Is the worldview complete?
Modern physics, which has categorically overlooked ontological questions, has now ended up entangled in them. What is dark matter? What is dark energy? These questions were rendered pointless by answering the primary questions: what is matter? What is energy? Dark matter, dark energy, entangled particles, the multiverse, and the action at a distance seem like flights of imagination compared to the reality we experience. Since the universal patterns of data speak for a single reality, the unified theory should describe and explain everything in the same way, that is, the way we experience reality. As we begin to ponder comprehensively, many a problem in physics becomes pointless or not a problem at all. Isn't it a relief that the dark energy and dark matter are not needed to explain astronomical observations when nothing remotely like them has ever been discovered? The greatest difficulty may well be that the thermodynamic theory does not concur with the current theoretical conceptions, even though its interpretations tally with the data. The atomistic tenet does not deliver, for instance, spectacular symmetries or elaborate equations. Instead, it grants concrete comprehension. Henri Poincaré saw that many truths assumed of scientific theories are in fact mere practices. Can we question the current paradigm? Do we have the guts to acknowledge that the contemporary cosmology with the dark matter and dark energy is a darker phase in the history of science, just as ancient cosmology with its epicycles and deference once was? When we say that quanta embody everything, we assert a worldview that includes everything. However, it's incomplete. According to the incompleteness theorem of Kurt Gödel, foremost logician, it is possible to pose questions about the universe that have no answers within the same universe. Although it makes no sense to talk about what cannot be addressed, those matters are inexorably erased. We may ask why there is something rather than nothing, but we know nothing about nothing. We cannot know anything beyond the universe. The photons are all there is. We may ask why the universe exists, but we have no means to answer. The dawn of the cosmos was an event, but causality does not reach beyond the first event. Asking what preceded the beginning, we wonder where the quanta originated, but our experience only tells us that they exist. This contradiction exposes our inability to comprehend below the quantum and beyond the universe. We cannot prove the truth or falsify of statements that are beyond our deductive system. The universe is the realm of our reality. The multiverse is absurdity. Thermodynamics has no room for fanciful many worlds interpretations. We may also ask why the universe comprises precisely the number of quanta it does, but this we cannot explain. Nonetheless, we may assume that a universe smaller than ours would not have, so to say, turned on. Other events too, such as boiling water and the birth of a star or a collapse of a neutron in the core of a black hole, required a crossing of a boundary. We may also suspect that the universe could not have been born bigger than it was, as then it would have begun to expand ahead of its time. Georges Lemaitre thought that the ancient universe was a primeval atom that evolved and is still evolving by fragmenting into the pieces. Now we understand that such a flows of events in more detail, since we know the structures and reactions of the particles and the void. Explanations, to qualify as explanation, must be of some substance and must relate to our own experiences, even if it implies that we cannot dissect any deeper into reality than the quantum and beyond the limit of our worldview.